Hello and welcome to episode 4 of Science with Jake. In this episode, we're going to keep talking about the action potential. We're going to talk about voltage-gated channels, and then the rising phase, the falling phase, and then the recovery/undershoot phase. Last episode, we talked about resting membrane potential, but in this episode, we're just going to talk about changes in membrane potential. You needed to know what that baseline level was, though, so that we can now understand when it shifts. 3, 2, 1, cue the green screen. As I briefly mentioned in the last video, we have these two channels called the voltage-gated sodium ion channel and the voltage-gated potassium ion channel. Voltage-gated just means that they are activated by changes in the membrane potential. When a stimulus reaches the axon of a neuron, which we'll talk about in a later video, sodium ion channels leak open slightly. And this creates a slight influx of sodium ions into the cell, which makes the charge inside less negative. Once it slowly raises from negative 65 millivolts to negative 50 millivolts, that is the threshold when the action potential begins. When the membrane potential hits negative 50 millivolts, suddenly the sodium-gated ion channel opens up, as you can see in this diagram, and sodium ions rush into the cell. That's why we see here that the permeability of sodium ions is way higher than the permeability of potassium ions. Sodium floods the cell, and suddenly it becomes way more positively charged. So it goes from that negative 50 millivolts all the way up to positive 40 millivolts. Amazingly, this happens in just a few milliseconds, and the action potential as a whole happens in about a fifth of a second. Now let's look at this diagram and talk about the term depolarization. That refers to the process of reversing charge in this membrane potential. Once this depolarization process has occurred, the final charge becomes positive 40 millivolts, away from that negative 65 that it began at. It's worth noting that this whole process is very similar to the firing of a gun. It's a good analogy to use because as we hit that negative 50 millivolt threshold, this process of depolarization, it is an all or nothing process. It fires, all the sodium rushes through, it cannot be stopped, and it is going to peak. And once we hit that peak, we then hit the falling phase, which we're going to talk about next. Before I go back to the other diagram, let's stay here and talk about what it means when it says pK is greater than pNa. During this falling phase, the permeability of potassium is way higher than the permeability of sodium. This happens because during the falling phase, those voltage-gated sodium ion channels that we have in the middle here become inactivated, meaning they're blocked. They're not technically closed, they're just inactivated, meaning they're not going to allow sodium ions to keep flowing through. Interestingly, it has to be inactivated because it happens so fast that the rising phase hits and then instantly needs to fall that these gates cannot close fast enough. So it's faster for them to actually just inactivate themselves. Meanwhile, the voltage-gated potassium ion channels become fully open, which we technically didn't mention, but they do start to open during the rising phase as well. But it's only during the falling phase that they become fully open, and they now allow this repolarization to occur. As you can see, potassium ions are still flowing through the leakage channel, but they're now also flowing through that voltage-gated potassium ion channel. And this allows the cell to, like I said, repolarize, which is basically reversing that charge again back to that negative 65 millivolts that we want to go back to. As you'll see in this diagram, though, it actually goes a little more negative than negative 65. This is called the undershoot. Too much potassium leaves the cell and it becomes too negative, around negative 80 millivolts instead of the ideal negative 65 to 70. This undershoot period is also called hyperpolarization. This final phase is also known as the recovery phase. You'll see that the voltage-gated sodium ion channels are now fully closed, and the voltage-gated potassium ion channels are still open, allowing that potassium to flow back out. Eventually, those voltage-gated potassium ion channels also close, and then the cell needs to realign itself to that resting membrane potential. And as we talked about in the last episode, that resting membrane potential is maintained by the sodium-potassium pump, as well as that potassium and sodium ion leakage that happens throughout the membrane. Remember when I said that this is kind of like the firing of a gun? This period, the recovery period, is also called a refractory period because it is like the reload period of a gun. The gun cannot be fired, another action potential cannot occur until the membrane potential resets. You know, I thought that video was actually going to take longer, but because we already talked about this membrane potential and the way that ion flow changes the charge, we pretty much had a good understanding to be able to just talk about these next phases really quickly. If you still have questions, feel free to rewatch the video, go back, think about those steps individually, because I did move a little bit fast. It's a lot of information, but if you've made it this far, great job. You've learned so much. Look at all we've done. This is an action potential. There's so much going on there, and you just went through it all. Great job. In the next episode, we're going to talk about synapses, which are just the gaps between neurons where they're communicating.